Hi. Okay. We're back. All right. So this is the overlay, the data set that I've given you in the overlay. You have everything but the instructor. This is my end of the cooking show, just in case I crash and burn and I need to show you something, which isn't going to happen. It's going to work flawlessly. Okay. So here's the data. This is the Malibu DEM, and I'm going to right click on it and go to properties, because this is what we always do. We explore our data. And you go to source, and this is where you find out what projection coordinate system and datum it's in. And I've projected it to WGS 84, UTM zone 11. And because of that, I know that my grid cell resolution is in the horizontal units of meters, because UTM is in meters. And each grid cell is about 9.5 by 9.5 meter resolution. All right, so we've done that. I've also given you the boundary of Malibu. So again, you know, you guys saw this last week. So this is the boundary of Malibu, and what we're going to do is use that as our mask in our model, so that all of our output is just masked to that boundary. And the cool new data sets that I've given you, and I'm going to take some time and review these, are soils and vegetation. Vegetation, polygons, and soils. So I'm going to go into the Word document, and I know David and other people have been interested, because last week I showed you how to get DEM data, how you actually get data. I mean, it's one thing when we do labs in the classroom, and I mean, Esri's labs always work perfectly. They have the data sets that work. You push the button on the Esri Academy and it works. My labs, you know, I get the data for you, I package it, I tell you what I want you to do and see. But the reality is that you spend a lot of time in the quote, air quote, real world, working with data, getting data to work, and doing data quality, getting data in formats that work with GIS. So there's lots of different, so last week you had a little taste of that using the National Map Viewer, and I explained to you what you need to do in order to get your data. You have to get your bounding box in decimal degrees, and then when you get it downloaded, you have to project it so that you can work with it. Well, here I'm adding in 2 new data sources. I'm giving you the Malibu City boundary, elevation, the DEM, and vegetation and soils. So soils, has anybody worked with soils data before? Mm. Soils and vegetation, and okay, so I think the DEM is the mothership of all environmental applications. But if you're going to do work with environmental GIS, vegetation and soils are the next important, along with meteorological data, which is a whole host of complexity in and of itself. So soils are collected by the National, it used to be the Conservation Service. Oh God, I'm totally blanking. I'm going to Google something for a second. If you Google StatsGo, StatsGo stands for State and County Soil. It's this soils, StatsGo soils. NRCS, that was the acronym that I was looking for, the Natural Resource Conservation Service. So the Natural Resource Conservation Service has mapped soils for the entire US. Unfortunately, they are at a scale of 1 to 250,000. So remember scale, large scale, small area, small scale, large area, very small scale, very coarse, and very lumped and not very detailed. But there are data at the soil survey level, but not for the entire United States. So this is something that is ongoing. Soil surveys are very large scale. So they can be like 1 to 12,000 or 1 to 62,000. And people go out and dig soil pits or use vegetation and figure out what the soils are for an area. And that's the data set that's most valuable. Now, for a while, this data was really, really, really hard to work with, because you had to there were like 100 different tables of soil parameters. You have depth to bedrock, percent silt, percent clay, percent loam, pH, what kinds of agricultural use it's good for, what you can use. Can you put a septic tank on there? What kind of fruit trees can you grow on there? I mean, anything you can possibly think of is in an attribute table for soils, but they're all in different attribute tables. So you would need to know the soil mapping unit and then join and join and join. And it was very unwieldy and very difficult to access. So that, if you go to the Soil Survey's website, it could take, it would be a long lab just to get the soil downloaded from here and get it to work. But the cool thing is what Esri has done is they've created this map package. So I'm just going to quickly go to their website, and they've made accessible soil survey data, and you download it as a map package and then you export it. So I've done this for you. I'm not going to have you do this in the lab, but here's the Surgo downloader if you want to get soils data. The thing is, you'll have blanks in here because it's not necessarily available for all study areas. But you go to the Surgo, which is soil survey level soils, and you go to the Surgo downloader, and you go view application. Oh wait, there's a way that you can click. Here's the Surgo downloader. So here are the different areas. So say your study area is Newport Beach, Irvine. You can download the Newport Bay map package and export it in ArcGIS. So it downloads as a map package. So you have to use a different conversion function. You download the map package and it puts the data in a geodatabase, and then you go in the geodatabase and you find the data and then you merge it with all the surrounding areas. So this in itself could be an hour of explanation, but I've done this for you. I just want to show you where I got it from. And actually, if you go to the Surgo downloader, you can, I think if I go to authoritative, there's a way that you can open it directly in Esri web mapping. Maybe it's from the Living Atlas. You can explore this on your own if you want to get more data. I know some of you are interested in where you get data. So the thing is, you download, I could go offline or work with you guys later, but you download, I know I have it on the N drive. Let's see, N data, soils. Here's Surgo. So you download it and it gives it to you in this map package, which you then export. So these are the map packages in ArcGIS, and you bring them in and they put them in separate folders, and then you find the basin that you want and you merge it together. Okay, so that's background on the soils data. And I'm going to jump back into ArcGIS and show you what this looks like. So this is the soils data for the Malibu region, and I open the attribute table, and you'll see there's so much information in here, and this is they've only provided some of the attributes that are available for soils data. So they have the mapping unit name, they have the mapping unit, what kind is it good for farmland, not prime farmland. They have all sorts of other things. Not everything is available in this data set. In other data sets it is. You have to go to the decoder ring to understand the decoder ring, meaning the attribute, the metadata for it, understanding what these different things, slope gradient, flood information, ponding percent. And then, so here are the attributes that I'm going to use in the lab today. You have drainage class, different kinds of drainage classes, and the hydrologic soil group. So these are what we use in hydrology for determining flood risk, and I'm using them in this context to determine or approximate how wet a soil might be. So if a soil is well drained, it means that it's probably more sand, right? So water, when it hits the soil, will infiltrate into the soil and percolate down. So it drains. So the assumption here is that it's more dry, and drier soils are more likely to burn. I mean, I know this, we could sit for days and argue what makes something a fire hazard, but that's the assumption that I took for this lab. So wet soils are less likely to burn. So what I did was add a field to the attribute table here called soil rank. And I ranked the soils based on how likely they were to burn, based on, I'm scrolling down to the soil hazard, based on this drainage class. So I did a whole bunch of select by attributes. If select by attribute on DR class wet is equal to excessively drained. If it was excessively drained, I calculated a value of 5 into that new attribute field called soil rank. If it was somewhat excessively drained, I calculated a 4. If it was well drained, I gave it a 3, and so on. So if it's poorly drained or somewhat poorly drained, I figured they were wet, they were least likely to burn, and I gave them a 1. So that's how I came up with the ranks for the suitability analysis for fire hazard for soils. So that's any questions on soils data. I know that was a quick tour of soils data, but I just wanted to introduce you to soils data and give you a little bit of background on how I came up with that ranking. So again, I went to select by attribute, and I took the soils. I did this all for you. So I have to find it now. There's so much in here, and it's not even part of what you could possibly find out about soils. Soils is such a rich data set. I'm looking for the DR class wet. If somebody sees it pop up, let me know. Oh, I skipped it. I'm sorry. Give me a minute. I just want to show you how I did this, because here we are, DR class wet. And then this is where you use get unique values. So there are the unique values. There's only 4 of them actually. So let me see. I don't know what I did my 5s on. So DR class wet is equal to moderately well drained, apply, and okay. So these are the ones that were selected, moderately well drained. I assigned a value of 2 in the soil rank. So that's how the soil rank was created. So that's my introduction to the soils data set. Okay, now going back to the vegetation data set to give you some background on vegetation. So vegetation comes from the Forest Service. So here's a link for all sorts of vegetation, and for California, I've given you the link for the CalVeg, and there's different places you can get this. I'm just gonna show you where I got the data, just in case.
When we get this kind of data, is that free, or is
it's all free? The US data, yeah, government data is all free. So here's the metadata for it. So this will tell you what the attribute fields mean in the tables. And go back to the Word document, and here's, hopefully this link still works. I checked the lower one. I don't remember if I checked this. These links often change too. Here's the Forest Service data sets. So you can download national data sets, and there's all sorts of data. I think I went to CalVeg. I can't remember exactly where. Stewardship, black beetle, ecological provinces, ecological sections, invasive plants. Sorry, I'm looking for the vegetation, CalVeg, watershed condition classification. This is all data curated by the Forest Service. So they give it to you in Esri Geo databases, existing vegetation, Central Coast. So this is CalVeg. So you can get the geo database, existing vegetation polygon features with classifications from a scale of 1 to 24,000 to 1 to 100,000. So you have the different ecoregions and the different, this CalVeg region 5 corresponds to our data set. So there's different ones for the different vegetation regions in California. And then you can get this from here. You need to go to the, I wish I hadn't closed the metadata, but the metadata will explain what the different variables are in the attribute table. And if I go into the attribute table for the vegetation, you have the ecoregion and all of this physiographic region, all sorts of information in the attribute table. And you also have WHR type, which is essentially a cover type. And you also have something called cover type, cov type, which I need to find. And that's what I based the ranking on. So here's the cover type: urban, barren, herbaceous, mixed, hardwood, shrubs. It classifies the vegetation in each of these polygons into these different cover types. So it's very, look at how detailed these polygons are. So you have these different cover types. You can tell actually that it was derived from a raster because it's blocky. It was derived, it said, from Landsat. I don't know if you caught that when I went through the CalVeg description. Landsat is the satellite. So it was classified from satellite imagery and ported into a vector with all of this attribute information. So the cover types that I selected for my fire hazard assessment here is, okay, if it's agricultural, I thought, it's mildly likely to burn. So I did select by attribute on agriculture, and anything that was agriculture, I gave a rank of 2. If it's barren, it wasn't gonna burn. So I gave it a rank of 1. If it's water, it wasn't gonna burn. If it's urban, I said it's probably not likely to burn. Shrubs, I said more so, mixed conifer less, herbaceous more so, and I gave the highest burn likelihood to conifer and hardwood. So this is something that, again, like you and I could sit for a day and discuss what should we do to rank them. There's actually something in, I don't know if you want to call it in the field of project management, in the field of management called the Delphi Method, which is an approach to bringing groups of experts together to come up with, and I'm sure they're doing this all over for the COVID stuff, bringing groups of experts together to come up with hazard, risk, whatever you want to decide. It's called the Delphi Method, and there's actually a procedure and a protocol for coming up with these rankings. Granted, we're in a class and you're just going to do it off the top of your head. So what I'm telling you is I pre-programmed, pre-decided for you for this lab, these rankings for the purposes of the lab. If you want to go off-road and go above and beyond and you're going to redo this analysis on your own and change some of the weighting schemes, but you're also welcome to go back into the vegetation data set and change these rankings. Go back into the soils data set and change these rankings if you want to go above and beyond. And I put in the what to turn in extra credit if you go above and beyond and do some of this to manipulate the data before you put it into the overlays. Any questions? So I've pre-programmed, program's not the right word, I've pre-processed and made some assumptions and edited the input data sets accordingly. So again, I've added fields to soils and vegetation. I added a field called soil rank, and I gave it the rankings of 1 to 5. And I've added a field to the vegetation, and I've given it rankings of 1 to 5. I actually just noticed an error. I think I may need to do 1 to 4s because it looked like soils was 1 to 4s, but we'll work with it, okay? So does everybody understand that? Hopefully. Thumbs up. Are you with me? Are you drinking your coffee? Okay. All right. Oh, Zoom. Okay, and then the last assumption that I've made for this part of the lab is slope. We've already calculated slope. We already know how to do that. And what I'm going to show you now is the reclassification tool so that you can do reclassifications on grids. And we're going to just take our slope ranges and reclassify them into 5 categories. So I've decided that anything that's, and because it's continuous, you have to take all of the values. So anything that's 0 to just up to 1, I'm making it as a no hazard 0. Anything that's a 1 to 25, I'm making it mild hazard. I'm saying low slopes, mild hazard, steep slopes, most hazard. Now you could get really more sophisticated with this, like they've done in this, I'm trying to find my slide. In this example, where they've taken slopes and they said anything that's 0 to 5 and 15 to 20, I'm going to give that a 2. So you can just either use Raster calculator or reclassify to do that. Anything 0 to 5 is a 2. Anything 15 to 20 is a 2. So you could make it more sophisticated, but for the purposes of this assignment, I'm just doing a straight breaks. Also a trick to this is sometimes you can use symbology. If you want to break things using quantiles and figure out what the quantile ranges are and use that to classify your slopes, like what are, in this study area, what is the flattest? That might be a more sophisticated way to do this. So you take your slopes and you explore your data first, and then you put your data in quantiles and use the quantile ranges, like the lowest 0 to 20% is going to be a 1. The 20 to 40% is a 2. You guys following me? Remember how we used quantile ranges to calculate population density? You could do the same with slope if you classify it. I didn't do that for this lab, but I could go off-road and show you how to do that if you'd like. And just to also, if you go do this on your own data set, I'm actually going to calculate slope. So I'm going to quickly calculate slope on this DEM. This isn't part of the assignment, but I just want to show you that I'm familiar, because I'm familiar from what we did last week with the DEM, we already know what those slope ranges are, and we know that the range goes up to 400%. So I'm going to go to Spatial Analyst Tools, Surface Slope. And my input is going to be the Malibu DEM. And I'm not going to call it the same thing that I'm going to call the other data, just so that it, oh, now my machine's really slow. We're going to have fun today. It'll be slow. I'm going to put it in 41 overlay, and I'll call it SLP, just to show you. And I'm going to make it percent. So this is, we're going to do this in Model Builder, but I'm just calculating, I'm creating a slope grid just to do data exploration before we actually get into the assignment. Do you guys have ArcGIS up now with the data there?
Yeah.
All right, so you have the upper, if, I don't know what's happening here. Everything's really slow. Well, when that's done, what I'm going to show you is how you can classify your slope grid and go, so here's slope. I know that my slope goes up to 379, so I know my range here goes up to 400, but if you ever did this with your own data, you'd have to calculate slope to understand the slope values in your data set and rank them accordingly. So if everybody understand how I did my slope ranks?
I didn't do it because are we gonna redo it on the builder?
Yeah, no, I'm just showing you this. Don't do it now. Okay, so but what I want to show you is what I was talking about if we wanted to use quantile. So I'm going to go to Properties and Symbology and Classified, and I'm going to classify it into 5 values, and I'm going to use quantile. And so this gives me the quantile ranges, just like we did with population density. So here, if I go to Properties again, so here, anything that's 0, I guess I should do it in 6 classes because it makes the 0 a class. I'm going to make it 6. Oh. Well, anything, never mind. I'm going to make it, I'll do it again. 5, classify. Let me make sure it's quantile. I guess I can do 6 classes and approximate that. So anything that's a 0 is no risk. Anything that's 1 to 22 is in the 20% range. Anything that's 22 to 37 for this data set is in the 40% of the slopes in this study area are in that range. 6, and then so on and so forth, right? So this is quantile if you wanted to use this for your ranking. So you could say 66 to 400. I'm just showing you different ways that you could consider ranking for fire hazard. It's up to you, like, right? So, but what I did for this lab is 1 through 5, just based on 0, 1 to 25 is 1, etc. So that's how I did the ranking. So all I've done here so far in the past X number of minutes of this lab part of the recording is explain the data. So now I've explained the data, and now we're going to do the overlay analysis. So I just wanted to explain how I got at the 1 to 5 rankings before we throw it into an overlay analysis. Why did I close that? Close the lab document. I'll open it up just so I can get to it again. Okay, so we're back in ArcGIS. We don't need this. I was just showing you, so I'm just going to remove it. Okay, now we're going to get to an overlay analysis. So are you with me?
Yes.
Okay, so we are going to right click, and you can put this in your student folder or right in the overlay root. We're going to right click on overlay and go to new toolbox, and I'm going to rename this toolbox while it's highlighted, and I'm just going to call it overlay, just so it's good practice to name things. Okay, now I have a toolbox, and in here is where I'm going to put my overlay tool. So I'm going to make a new model or a new overlay model. And this one, I'm going to go to model properties, and I'm going to call this weighted overlay. And I'll give it the name and the label the same thing. So important, store relative path names, right? And now we're going to set our model here. You can put in a description, and you can be, I just recommend you be descriptive every time you do this, but you can say GEOG 481, fire hazard suitability ability analysis, and then you have your criteria. You want to be as specific as possible. Veg, right? So I'm not going to take time here. I'm going to have you guys do this, but you would go back and fill that in. Okay, so in the environments, we're going to set our processing extent, our raster analysis, and our workspace. So I'm going to check those boxes and then click values. This is what you always do when you build a model. You go to the properties first and set the environments for the overarching model. So our workspace, I'm going to set to the output folder for this lab, overlay output, and same for the scratch. So it's always going to throw things into the output folder. The processing extent, I'm going to set to Malibu DEM, just so it's out to that extent. And raster analysis, I'm going to set to Malibu DEM, and the mask, I'm going to set to the Malibu Polygon, just so it clips it to that. So I've set my workspace to output, my cell size to the same as the Malibu DEM, and the mask to mask it and clip it to the Malibu Polygon. So this should be second nature to you guys already now that you've worked a few times with Model Builder. So we've set our values for our environments. We've done some general stuff, store relative path names, and apply and okay. And now we're ready to build our model. So I'm going to drag in the data set. So I'm going to drag in from my table of contents, the Malibu DEM, the soils, and the veg. I'm going to go back into my Word document so I can follow my instructions about what I do first. So I talked about the rankings, open a blank map, connect to the folder, rename the toolbox overlay and call it weighted overlay. I have in the Word document the environments, and now we're going to create our rank grids. So first I have you take the vegetation and we're going to convert that from a polygon to a raster. Same with soils on the, okay, so the first thing I have you do is use the, remember from 2 weeks ago, the raster priority? We converted the Orange County land use to a raster based on that LU code. Here we're going to go to conversion tools to raster, polygon to raster. So I'm going to drag this in twice, but I'll just do it first for the soils. So I'm going to click polygon to raster, and my input is soils. And the value field's so important. This is the most important thing. You want to grid it on the soil rank that I had in that attribute table. And this one will call, and this is another trick. You don't have to like dig deep into your folder structure. Just call it soil rank and type in the name that you want in the output there, and watch what happens. Because I set my scratch space and my workspace to my output folder, it automatically gives it that, that location. So just type the name of it. And that way you don't, by accident, hardwire your output to some other drive that, like the C drive, and otherwise it would, so it reverts to the overarching scratch and workspace that you set in your properties. And if you hardwire it to somewhere else, it will mess up your model. So you want to always just give it the name. Does that make sense? Give it the name here, and then it'll put it where it's supposed to go. So we've got our soils and we're gridding it on soil rank. And now we've got a raster called soil rank that's going to be in a range of 1 to 5, hopefully. I think maybe it's 1 to 4, but okay. Now I'm going to bring in the polygon to raster and do the same thing. The input is going to be veg. The feature ID that we're the value field that we're gridding on is veg rank. So important. And this one we're just going to call veg rank. And now we have a raster of vegetation, and instead of 0s and 1s, it's 1s to 5s. And then finally, we're going to calculate slope and percent. So I'm going to go into my Spatial Analyst tool, slope, and drag in the slope tool. And the input is Malibu DEM, and the output raster is SLP PCT. And you want to make sure that you make it percent rise, okay? Can't, because don't forget to do that. If we're thinking in percent, we have to, if you want it in degrees, make it degrees, but I'm making mine percent rise. Apply and okay, and now we have a slope grid. But before we can throw it into the overlay, it's not ranked yet. We have to do one more step. So I'm pulling these down just because they this isn't there yet. We need to bring in that reclassify tool. So here's a new tool that I haven't shown you yet. So here's your chance to get to use the reclassify tool in the Spatial Analyst toolbox. Where is it? Here, reclass. So there's this whole set of reclass tools, and the one that you want is reclassify. And I'm going to go back into the Word document. Oh, maybe not. I don't know. I just screwed this up. So we've done step 10, we've done step 11, and now we're doing step 12 and 13 in the Word document. So I have all this in here for you to fall back on. We're going to select slope percent as the input and then reclassify. So reclassify is a little bit annoying and picky and sensitive. It says my internet connection is unstable, so if I lose you guys, I'll do my hotspot. So just, am I out? Can you hear me? Okay.
Yeah.
Okay, let me know if I get tinny. I had problems yesterday. So I'm bringing in the reclassify tool. When you double click the reclassify tool, you put your input raster is slope percent. And I know you have to add entries for each of the values. And so I have you add 6 classes because the first class of 0 to 1 is going to be zeros. So you just click this add entry 6 times. So 1, 2, 3, 4, 5, 6, and it adds old values to new values. And the key here is the reclass field must be on value. It doesn't give me any other options. This is where it's picky. So I have to type in here 0 space dash space 1, and the new value is going to be 0. If I don't put the space in between here, it doesn't work. Like if you just had it 0 like this, the tools, you're going to run your model and you're going to be really annoyed because your tool's going to crash and you don't know why. It has to have these spaces in it. Programmers, right? And so forth. So it's 1 to 25, 25 to 50. So I'm going to do 1 space dash space 25. 25 space dash space 50, 50 space dash space 75, 75 space dash space 100, and 100 space dash space 400, because I know my scale goes up to 370 something. So the other thing is, whoops, this is 100. I don't do 101. Like I don't do 0 to 1, 1 to 25, 26 to 50, 51 to 75, because otherwise you'd miss all of those floats that are in between. We're making a ranking of integers, so we have to capture all the ranges in there. So that's why I'm duplicating the values on each end. So this is 0, 1, 2, 3, 4, 5, and this, I'm just going to get rid of all that and just say SLOPE rank, slope rank. So does that make sense? This is how you reclassify. You have to add in the entries and then do old values to new values. And what it's going to do is create a grid of 1s to 5s based on this reclassification. And this is what you can alter as well. So I'm going to apply and OK. And now I have all my ranked grids of 1s to 5s. So now I've prepped the data for you. You can tell that there's a lot that went in behind the scenes to get these ranked grids. And now we're ready to do our overlay. So any questions right now? Okay.
No.
I'm going to add in weighted sum, and we'll do weighted sum first. So weighted sum is what I showed you in the slides. All you do is put your input rasters in, and it's so important that your input rasters are the ranked ones. So I'm going to take soil rank, veg rank, and slope rank. And this is where I apply the weights. So say I want slope to be 40 times more than anything else. I mean, that would multiply the whole slope grid by 40. I'm going to go back into my Word document because I forget what I told you to do for the slope rank. I did 3s for vegetation, 2s for slope, and soils for 1. So vegetation is 3s. I said it was 3 times more important. Soils was 1 and slope was 2. I mean, you can make this 5s or 6. I mean, you could change your ranking. And this would be, I'm going to call it W sum, weighted sum. But you could do this like 5, 10, 15, 20 different times and get 20 different outputs based on your different rankings. So I'm just, and you could do this in Raster Calculator too. You could do all of this in Raster Calculator, but it's a nice, nifty, easy to access tool that they've programmed as part of the overlay box. So that's simple. That's weighted sum. It's simpler to understand. I mean, binary overlay is the easiest to understand. This basically, you're taking your grids, you're ranking them and multiplying them by a multiplier. Question? I'm going to apply and okay. So now I have a weighted sum. Okay. But now we're going to, any questions on that? I'm going to bring in weighted overlay and let's see what weighted overlay does. Weighted overlay is also picky, and you need to, there's a lot more to these tools. I'm going to open up the tool. I want you to, on your own time, actually go to the tool help and read a little bit. Oh, that did something weird. It opens up Arcgis Help, and there's so much really good background information, and I have some links to some more information in the lab. But it tells you what it does in Spatial Analyst. It talks about the evaluation scales. It talks about reclassifying. So it takes your input ranked rasters and assigns a % influence to them. So in this example, so basically it's multiplying every value in that grid by, say this, in this example, the % influence is 75 and 25. So it's taking your 1 to 5s and multiplying it by 0.75. And it's taking your other grid and with the influence of 25 and multiplying it by 0.25. So it's scaling everything and then adding it back together. So everything at the output is still 1 to 5, but it's weighted or scaled by a weight that you assign to it, a relative influence. So it's not that complex, but the interface is a little picky. So that's weighted overlay. So there's more in the help about it. So when you open up the tool, this is where you can set equal influence. This is where you should read more behind the scenes about what the tool does. Balances the % influence, but we're going to do our evaluation scale. Because we already ranked these grids 1 to 5, our evaluation scale is 1 to 5 by 1. So we've already done that. If you're bringing in data that you didn't rank before, weighted overlay allows you to rescale it, especially if it's continuous data, and assign ranks that way. So it has functionality that way, and that's built in here, which makes it a little bit more unwieldy with the interface, and I'll show you what happens. So I first change my evaluation scale 1 to 5 by 1, and then I have to add in each raster separately. So I'm going to add in my ranked raster. So I'm going to bring in soil rank, and then I'm just going to add in, and it does this weird thing. It didn't do this to me yesterday. I'm going to do veg rank, and I'm going to add in slope rank. And this is where you have to do like some weird, like, I don't know why it does this. It assumes that it has a rating. I don't know why it didn't capture the 1 to 5 by 1. So it automatically put it into scales of 1 to 9. So we just need to select in these that are above restricted. So anything that's above 5, because we don't have those values, you call it restricted. So you have to, I did this 2 different times and it came up differently. So you just change the values. So 1 is a 1, 2 is a 2, 3 is a 3, 4 is a 4, and 5 is a 5, right? We have already done that. So you have to just you have to force it into the values that you've already assigned. So in the vegetation, 1 is a 1, 2 is a 2, 3 is a 3, 4 is a 4, 5 is a 5. And see, we know we don't have anything greater than 5. So anything that's a 6 or 7, we're just going to assign restricted. I don't know why it has these values in here. So it's just not going to process these, and it has a no data in here. And then you have to scroll down. So now we have a matching of our ranks. And then we're going to scroll down, and I'll make zeros, 1s, 1, 2, 3, 4, 5. So we're okay with our slope. So this is going to be, what did I tell you to call this? I think I told you to call it just W overlay. But we haven't set the evaluation scales, and this is the most important part. This is the percent influence. So this is where you divide it by, multiply it by your percent influence. So in the lab, I suggested 40% for slope, 25 for soil, and 35 for vegetation. 35 slope. What did I say? 25 for vegetation. What did I say? Oh my gosh. 40 for slope, soils is 25, vegetation is 35. It gives me an X because my overlay is wrong. Soils is 25. It doesn't add to 100, it adds to 60, so I need to make 40% for my slope. So when I put in 40, that X is going to go away. The percent influence is going to be up to 100. Does that make sense? It's kind of a finicky interface, but this is how weighted overlay works. Restricted assigns, like if it's not there, we're just forcing it into these ranges. And now I have my weighted overlay. So a lot of complexity here. It's a very simple model. I'm going to save my model, and actually this is a good time to save your MXD, and I'm going to call it I'll call it overlay demo, something like that. And before I run my model, I'm just going to right click on W sum and W overlay and say add to display. So when the model is done, it's going to add these last ones to the display so we can look at them. So I'm going to run my model. You guys good? Ready? With me? Oh, my screen is frozen. Are we back? Oh,
Yeah.
sorry, I just saw that. That was so 10 minutes ago.
Yeah, it was for a while, but it's back.
What did you miss?
I'm not sure anymore. It was in the beginning.
Okay.
I forgot already.
All right. Well, I'm
But
running.
I'm following because it became too hard to go back and forth, so I'm just watching and then I'll do it later.
It was probably when I had that internet connection issue.
Yeah.
Well, you'll have the video of this part of the lab. So it's
Yeah.
running this, and we're just going to look at the weighted sum and weighted overlay. I just want to give you guys a sense of the different complexity that's available. So it went pretty quickly, and here's my output. So based on, I'm going to save this. I'm just going to close it. So the result of weighted overlay is 1 to 5. So 5, you could change this. I'm going to go to properties. I think I want to just reverse my color scheme. Just want to reverse the ramp. I forget how to do that. I don't remember. I'm going to make it like, I don't know, blues to red. So red is the highest fire hazard. 1, 2, 3, 4, 5. So that's my weighted overlay. So I have lower fire hazards here, and then in these areas, it's the higher fire hazard. If somebody wanted to, if you go to properties and you wanted to find out what is the area and the highest fire hazard zones, you take the sum of these grid cells. So there's 277,004 and 1,935 and 5. Add them together and multiply them by the grid cell resolution. It would give you the total fire hazard area in Malibu. You could also bring in other data sets and see, okay, well, what buildings are impacted by the highest fire hazard, or which block groups that are in sensitive groups. I mean, you could expand the analysis, but this is just very simple. And just to prove, just to demonstrate also, it's the same data sets, just different weights, different input assumptions gives you different results, different fire hazards. And here's the result from weighted sum. So weighted sum, I'm going to change my range here. And I'm going to classify it from, what did I pick? Where's that one? Is this the one that I used? No, it was blues. Oh God, I totally missed it. Oh, it's because it's up here. It's somewhere. Oh my God, I've totally lost it. This one. So low values are blue and red values are higher. And notice the range. So remember we multiplied 1 by, I can't remember what it was, but the highest value possible is 30 because we multiplied one grid by, I have to go back into my model. We've multiplied vegetation by 3. So vegetation became 15. The highest value in vegetation was 15. The highest value in slope would have been a 10 because we multiplied that grid by 2. So 25, and then the other one was just 5. So the highest possible fire risk would be something that's a grid cell that's 30. So you can see that you have 25s to 30s here. Now the interesting thing here is that I want to show you and that I talk about in the lab is we can't get the count. When something is a float grid, you can't get the count. In order to figure out that rank, not the rank, if you, the number of grid cells in each criteria, you have to convert it to an integer grid. So I added a little step at the end here where I show you how to convert your output to, did I? Oh, I do it in the end. I do it with the fuzzy overlay. I'm going to do it here, but basically you do it in Raster calculator. So we multiplied the grid by 1 and make it an integer, and then we can pull this information out and you can classify it. I'll hold off and I'll do it when we do the fuzzy overlay. But that way you can find out, okay, or you could just reclassify it in quantiles again and find out, you know, what values are in what range. So any questions before I move back into fuzzy overlay?
Yeah.
So that's quantiles and showing you where the highest percentage of fire hazard area occurs in that range. But if you wanted to count what those were, I guess I could do it now. You go, I'm going off a road here. A raster calculator, you would take integer, I believe, let me test. I could crash and burn here, but you convert it to an integer. So you take integer, which one is it? W sum. And then I'm going to multiply it by 1. So we have a grid. You're just multiplying it by 1. And I'm just going to call this, because I'm outside of my model, I'm just going to put it here. W sum I for integer. And let's see if that converts it to an integer so we can get the classes. I'm not sure. Yeah, it does. It converts it. Oh, you know what you want to do actually is multiply it by 100. That way you can rescale it back to decimal places. But if I go to the properties here, it's an integer grid. If I go to, now it has an attribute table, so I can find out, well, how many are in 19 or 20 or between 20 and, how many grid cells are between 20 and 29, the highest range, or 20 to 29 was the upper quartile range. And I go to count and I can do statistics on this. It tells me the total number of grid cells in that range, and I multiplied that by 9.48 by 9.48, and that gives me the total area. So hopefully you guys are with me with that. And those are the two weighted overlays, weighted overlay and weighted sum. And that's the output. Cool. But it's raster and we can get more complex, and that's the next part. So I can stop the video here and then go back to the fuzzy overlay, and I'm going to go back into the lecture notes. I'm going to talk about fuzzy overlay, and then we're going to redo this with some different assumptions using fuzzy overlay. So I'm just going to stop the recording now so that we have separate blocks for you to reflect back on. Would that work?
Yeah.
Okay.
Yeah.
And then I'll start it again. I'm getting the hang of this Zoom thing. Realizing that like a 3-hour long Zoom lecture is not useful.